So welcome back, everyone. So it's a pleasure to introduce Michael Anderson, who was also a GSI for this class a couple of years ago, and he's responsible for those great speed-ups I bragged about, using communication avoiding algorithms for tall, skinny QR on GPUs that you saw. But today the topic is going to be different. It's going to be about a different kind of pattern. It's how you glue together all this computational patterns you've been learning about into bigger codes and make them parallelize in an effective way. And what are the patterns that come up over and over again for that organization? And which is a big project with Mike's advisor, Kurt Koitzer, Tim Mattson of Intel, and a whole bunch of other people. And I believe there was also an announcement about the class project proposals. So we'd like to see a one-page draft early next week so we can read them carefully and give you feedback during spring break when things are relatively calm, and then we can iterate on what might be a good class project. Anything else? Okay.
Thanks, Jim, for the introduction. Okay, so I'm Mike Anderson down here, and I'm talking about architecting parallel software using patterns. And these slides are from my advisor, Kurt Koitzer, and also Tim Mattson, and the rest of our team. We've all contributed to this presentation. OK, so parallelism is a big challenge, and that's part of the reason probably why you're taking this course, is that it's becoming more important as time goes on. Even your cell phone, this is a Tegra 2 system on a chip. Your cell phone has a lot of parallelism. There's an SoC with a lot of different hardware blocks in there, DSPs, GPU, general purpose processor. Even within the general purpose processor, it's a multi-core with, and some ARMs have vector units. So that's just in your cell phone, not to mention GPU, like NVIDIA processors, these high-end discrete GPUs that can get up now, I guess, up to 4 teraflops in performance. And the ground is kind of shifting beneath our feet because these new processors are coming out all the time. For example, this Iterator processors that change the way we need to form our parallel code. So this is motivating. This is an important problem, parallelism. So I want to talk about parallel programming, and starting with an approach that doesn't work, and it's the intuitive approach. Then use that to motivate our solution, which is to architect parallel software using patterns. Then I'll go through specific individual patterns and describe each one with examples, and talk about computational patterns and structural patterns as well. And then finally, I have high-level examples of architecting application with patterns for speech recognition. And interrupt me at any time with questions. Interactive is very good. OK, so first is how not to write parallel code. So intuitively, I think certainly what I would gravitate towards doing when I started would be to take your initial code, run it through a profiler, get a performance profile, look at the hotspots, and if there's a hotspot, you can add threads and add concurrency. Hopefully it goes faster. Profile it again and kind of play whack-a-mole with these different parts of your code until it's fast enough to ship. So what's the problem with this? Lots of failures, meaning that you're introducing a lot of complexity into your code, and it might just stop working, or you might introduce bugs that are going to show up later after you ship it. And also, the big deal is, for me, is that it doesn't actually get faster in a lot of cases. So you introduce all these threads, and if you don't do it in a smart way, you could actually get a slow down instead of a speed up. And in fact, one of my colleagues began doing this approach to parallel programming for an EDA problem called Steiner tree construction or for routing. And so he found the hotspot, which had to do with routing each net. There's tons of nets in a circuit. You want to come up with a routing. And so he added threads, and this is the speed up down here. It's pretty much no speed up. So even with 6 threads, you're not getting a 6x speed up. In fact, you're getting a 1.01x speed up. So this kind of motivates why we want to think about the problem differently. And so why doesn't that work? So you can think, when you're doing that process, what are you thinking about? You're thinking about threads, and you're thinking about interactions between threads and locks and semaphores, and sharing data and so forth. So you're kind of focused on a very narrow subject, as opposed to thinking holistically about the structure of your application. So what's the alternative? How can you do any better? So first, I want to motivate the alternative and then present it to you. So we want to think about software design in general, not just parallel software design, but all software architecture. And I haven't been in industry for 15 years, and I didn't manage 25 software products. Kurt did, and so the takeaway that this slide is trying to convey is that if you want to figure out what makes one software project fail and another succeed, it's not that one software project chose the right language and the other one chose the wrong language or the right software environment. However, if you choose the wrong software architecture, that can kind of critically kill your project early on. Whereas if you choose the right software architecture, a lot of things just fall out of that. So where do you begin thinking about software architecture? So this slide is from Grady Booch, who is an object-oriented programming software architecture guru. And he created an analogy here where creating software is like creating a structure or a building. So in the simplest case, if you're creating a doghouse, you can do that one person, you can do that yourself. It requires a little bit of modeling, simple process, and simple tools. So it's analogous to a very simple software project. But as we get more sophisticated, you want to build bigger houses or bigger software. You need to do it with a team. You're going to need more sophisticated modeling, a well-defined process that everyone agrees on, and some more sophisticated tools. So in terms of software, what does this mean? What are more sophisticated tools? Well, in the 90s, there was a lot of work in software architecture. And this book called Software Architecture by Garland and Shaw enumerates a lot of different what are called architectural styles. So pipe and filter, for example, which is shown here, object-oriented programming, layered systems, agent repository, and process control. And this gives us a sense of structure in our software, and it allows us to scale it up and to more complex designs while still understanding what's going on. And it's analogous, if you think about building a house, it's analogous to different kinds of houses, such as ranch house, colonial, or a bungalow. This is the analogy. And then the goal, of course, this is again from the software engineering talk. The goal is, what do we need to do to build the building of the future, which is just enormous. We need advances in materials and analysis, so better architecture, better tools, and so on. And the big idea in software architecture is modularity. So we all know modularity is a great idea. Modularity helps a number of different people. It helps the architect of this. Yeah?
So maybe for the audience, you could just say a little more about what modularity is.
Sure. Oops. So modularity is the process of breaking a large design into smaller, understandable parts that can be described, implemented, and tested independently. So we were all kind of taught this, obviously, in our undergraduate software class to do a good job of making your design modular. And there's a number of reasons it makes, if you're the one at the top architecting the whole project, it makes things a lot more comprehensible. As a project manager, you have discrete parts. You're able to assign things to different teams, to different people. And you're able to track development, create a Gantt chart for each module. And as an implementer, you can focus on just your part without having dependencies on others. And it can also help us identify invariants and key computations, so things that always need to be true, and we can check that. That'll help us make sure that our code is correct. And without modularity, it's spaghetti code. That's the alternative. So we all know that how hard that can be. When you have multiple developers working on spaghetti code, it turns into a lot of discussions about what it's supposed to be doing. You can have dependencies with other people, so you can't continue until they're done. It's a bad thing. You have the issue where someone checks in code and it breaks everything, including your code. That's really common. And it's hard to write unit tests. Unit tests are kind of uniformly a good idea, but you can't do that without modularity. And finally, it's hard to parallelize, because if it's a huge chunk of code and you haven't identified key computations, there's a matrix multiply stuck in there somewhere, but you don't know where, then how are you going to optimize this? And this is a very old idea in this kind of classic ACM paper from the 70s describing modularity. OK, so object-oriented programming in general was very, very focused on creating good modularity, data locality, on architectural styles, and on design patterns, like the Gang of 4 design patterns. But a lot of things were neglected, such as concurrency, computational details, and fast, efficient parallel implementations. So this is to say that object-oriented programming doesn't solve all our problems when we're talking about writing parallel code. So going back to the analogy with Grady Booch, where he's saying that software is a building, and we need these tools of architecture in order to build larger and larger structures. The question is that the right analogy? Is software a building, or is it a factory? Is that a better analogy? So does anyone have an opinion? And you can tell me, and then we'll discuss. What do you think?
It used to look more like A, and now it looks more like B.
OK, so you said it used to look more like A. Now it looks more like B. So why did it change, you think?
As we saw,
Awesome.
as we saw from yesterday's talk, the existence of modules and frameworks makes the B model both faster in implementation and faster in execution.
OK. So faster. I mean, faster being more important, makes you think that. So why is faster more important? Was fast always important, I guess?
Well, I meant fast both in creation of a program and fast in the program's execution.
OK.
Ease of creation and then quality of product produced.
I see. All right. So you say factory. Anyone else have an opinion? So what's different between these two analogies? Like, what does a factory have that a building doesn't?
The factory makes carbon copies of the same thing.
OK. Factory makes carbon copies of the same thing. All right. So it churns out products, I guess, is what you're saying. And it takes in materials. So to me, when I think about the software, at least that you're interested in this class, it's a lot of high-performance software. You take in a lot of data. You spit out a lot of results. it reminds me of a factory. So that's interesting because what that means is that the machinery in the factory matters. Oh, sorry. So the machinery in the factory matters, and it's something that we want to pay attention to now, given that we really care about computation, especially in this class. Okay, so what is the machinery, I guess, was the open question. So as I said, I think this class has always been very focused on high-performance computing, and certainly the people here and also Berkeley Lab are experts in this. High-performance computing people know a lot about computations and parallelism and concurrency and performance, efficient programming, a lot about math. And that's something that's been missing from software architecture. So a couple years ago, I'm sure you're familiar with this paper and series of results from Phil Colella that identified these 7 common computations that happen across all of scientific computing. So basically, he's saying that if we can do these 7 computations very well, very efficiently, then we should be able to do pretty much most of the applications that we worry about at Berkeley Lab. So this is very interesting because he's creating a classification of computation, which is something that probably we haven't really thought about in the past as much. So this led then to a little bit of expansion of that idea into more than just the original 7 computations, but a few more that were added by professors here. And what they did was they considered a number of applications that they were experts in, such as databases, machine learning, HPC, well, we talked about HPC, but computer-aided design, and also these kind of emerging applications. And they identified where do the computations occur in these applications. So what they're doing is kind of creating a set of atomic units of computation that can be used and composed to solve these applications. But what about software architecture? So this is a great advancement in understanding computation itself. This is the computation. But what about the architecture that houses the computation? And sometimes in high-performance computing, it's easy to neglect software architecture and just kind of, if you're very, very focused on computation, to just put that all in sort of a monolithic architecture and kind of not worry about things like object-oriented programming principles and so forth. Of course, this isn't true all the time, but it's easy to do this when you're just focused on computation. So then the insight is what we want to do is find an approach to building software that gives support both to the one extreme, which is entirely worried about modularity and software architecture, combine that with the other extreme, which is entirely concerned about computation, and merge those two fields, merge those two concepts. Okay, so that motivates kind of the solution which I'm going to talk about now. So to start out, what I said is we're architecting software with patterns. So what is a pattern? So in the 70s, there was a book by a civil architecture professor here, who's pictured here, named Christopher Alexander. And what he did was he created a book outlining how you would not only build houses and structures inside of a house, but also entire cities and towns and road networks connecting cities. So kind of how would you architect the entire world? So it's a very ambitious problem that he's trying to solve. and if you're going to be that ambitious, you have to be a little bit vague. So he designed it in a way called a pattern language, which is a set of patterns, and each pattern is a problem combined with a solution. It's a problem-solution pair. And you describe the problem, and then you describe the solution, and the solution is a little bit interpretable. So as he says, you can use the solution a million times and never do it the same way twice. So in this book, there are patterns for example, how to build a roof cap to how to distribute towns, distribution of towns. So just some examples. And this then gained a lot of traction in software architecture as well, because it's an interesting way to think about how you design things. So why are patterns useful? Well, first off, they give us a vocabulary for important elements of design. And that helps us teach design. Take the principles that you know from building something many times, and you can transfer that knowledge effectively. It also gives you a sense of finiteness. So if you know that there's only 12 ways that people really do this, that makes your life a lot easier, because you're not just constantly encountering new approaches. You can kind of classify them into finite groups. It also guides design, because when you read these patterns, it's not just a name. It's also really a description of the whole problem and tips and tricks for how to implement it, including typical problems that come up, like bottlenecks. And finally, it helps you document your design, and so people know what you're talking about. And as I just said, yeah, in the patterns, when you read them, and we have a number of them for software, for our parallel patterns, useful implementation techniques, and then a list of bottlenecks that people have run into every time they do this, so they give you a heads up. Okay, so this is not only, this is our list of patterns, but it's also, so on the left side, there's software structure patterns. So that comes from what I was talking about in the beginning, from object-oriented programming and software architecture. So I'll go through these later in the lecture. On the right side are the key computations that come from the dwarves that you've been learning about all semester. And the way that you architect is by identifying software structure in your program and then filling in the gaps with where the computation happens with the type of computation, or with even more structure and more computation, and so forth. So it's a back and forth process, and you kind of create this hierarchical architecture. Okay, so the structural patterns, as I said, are how you identify structure in your software. So they include pipe and filter, agent repository, iterator. Some of these I'm sure you're very familiar with. MapReduce, layered systems, and process control. They describe the structure, but not what actually happens. And the analogy, going back to the building and the factory analogy, this is like the layout of the factory. So you want to design your computations so that data flows from one to another, and identifying sequences of computations and also independent computations as well. So the second part is identifying key computations. So that you go to this. So for each one of these, we have a set of descriptions, and you have the lectures from this course as well. And once you identify a computation, there's just been a ton of work telling you how to implement that efficiently and which libraries to use. And going back to the analogy, the computational patterns are like the machines of the factory. So when you're done architecting, you have something that looks like this. You have a structure telling you how your computation's oriented and how your data flows. And in each node of this graph, you have some information about what is actually computed. And the interesting thing is that when you look at, if you were a factory manager, you would worry about similar issues that we worry about as software developers, so, or as at least parallel software developers. So things like scheduling, latency, capacity, and load balance are all things that you would worry about inside of a factory. Okay, so to summarize, we're going to spend the rest of the lecture architecting parallel software in this way by identifying structure, filling in the structure with computation, kind of a recursive approach. And that's in contrast to what you're thinking about, essentially. The idea is what you're thinking about when you're designing your software should be things like this, and you should not be worried about lower level details like concurrency issues. And to summarize, what we're trying to do here is to integrate the ideas of structural orientation of software with the insights from high performance computing, so that you're thinking about this when you're writing your high performance code. Okay, so next I'm going to talk specifically about each pattern and give examples and hopefully more interaction, and then give an example on a full application at the end. But we can probably take a break, I think, or yeah. You can take like 5 minutes. So. Okay.
Any questions?
Questions?
So let me say that for your final projects, when you do the write-up, if not in the initial proposal, what we are going to ask you to do is to describe the architecture of your overall implementation that you're doing in this language. Give it a try and see if you can describe how how you would break down the code that you either write or use in this way to help understand where the bottlenecks are and whether it's well organized. This is language and we'll see you.
All right. So now the fun part where we talk about the actual patterns. So here's our inventory, and I'll go through 5 of them. Pipe and filter, iterator, MapReduce, agent repository, process control, model view controller, event-based coordination, puppeteer, and static task graph. So what is a structural pattern? Well, you can think of it like a graph, and it's composed of components, which are where computation happens, and connectors, where communication happens. So if you configure this graph with vertices and edges, then a structural pattern is not a specific graph, meaning it can have a lot of variation, but it's kind of a family of graphs. So you'll recognize it when you see it. Specific graphs correspond to specific structural patterns. So the first pattern is pipe and filter. And this is the most, not the most general, it's a very general pattern. We have filters, which have computation in them, pipes that connect filters and transfer data. Each filter processes its inputs. It doesn't carry any state, and it generates output. And we can have some feedback in our filter as well. But can anyone tell me an example of an application that you think follows this structure? MapReduce. Well,
Some imaging applications.
is imaging?
Imaging, yeah.
Imaging? So can you be more specific? What kind of imaging?
Microphone. So you apply a bunch of filters on images first and then compute some features. And maybe let's say using those features, you can determine the distortion in the image, and then you want to autocorrect the image. So you have a feedback, then you can put that in the loop and keep improving the quality.
Perfect. That's very perfect. So you're saying, yeah. So you said it. You can pass images through these pipes, apply filters to the images, and then it's literally a filter as well. So that's a great example. Is there anything else? Any other ideas? So pretty much most applications at some level are like this. You can just draw a sequence of computations that happen. So at the very highest level, I think most applications follow this.
As long as they're stateless.
Oh, as long as they're stateless, yeah. Exactly, yeah. So your imaging example is good. So we have an image, one example, image retrieval system where you're actually doing some machine learning. You pass in some images, as you said, do some feature extraction, pass it into a classifier, and so on. But another example is a compiler. You start with a program source, do some lexing, some parsing, build an IR. You might want to optimize the program, so do transformations on the IR. Generate code, have some object code to execute. It's a great example. And then a logic optimizer, which is kind of like a hardware compiler. You start with a netlist, which is a description of a circuit. You scan it and build an IR, and then you can do optimization passes, maybe to optimize for energy or for latency, frequency. So, very general pattern. Next is the iterator pattern, which I'm sure you all know. You come in to the top and check your initialization condition. If it's true, then you execute the body, the loop, and then there's an exit condition. If it's not met, you continue to execute the body. If it is met, you fall out. So this it's very simple, but it adds a lot of power. So can anybody tell me an application that uses this kind of at a very high level, you think? Okay. Oh, I'm sorry. So don't be confused with this stuff. That's just in there to demonstrate that there's some computation. But the pattern itself is just the concept of iteration. So some application where you essentially are performing something iteratively and you have a specific condition you check.
If you have an iterative method to solve for like eigenvalues or something.
Perfect. Yes, iterative solvers, and I think you talked a lot about that in this class, about
They'll come up later too.
Okay, solving AX equals B or finding eigenvalue. That's a great example. So essentially, you have some guess for X, and then you update X, you update your guess in the loop, and then your exit condition you'd be checking some kind of residual, that's very common in iterative solvers. So that's a great example. Our example that we encountered is also an iterative solver, but it's for SVM training an SVM classifier. So you have a number of points, and you want to build this frontier that divides the points. The surface is the frontier, essentially. So you update your surface, and then you have to identify points that are outliers in order to process those. And you iterate until the surface is acceptably close to the optimal solution. That's great. And the third one is MapReduce. And the framework from Google everybody knows about this. It's what you do, but it's also something that's used in, for example, in Python, you can do MapReduce. In functional programming. So what you do is you map a function onto a set of data. Then for each data element in your list, you perform that function. And then that's passed into a reduction stage where you define how the data is reduced. Maybe it's summed or you do a max function or something like that. So this is incredibly common, but can you think of some applications where that look like this at a very high level?
Computing histogram of counts on data.
Okay.
Frequency.
Okay, so frequency of counts. So in your map stage, I guess you're mapping over documents, say?
Yeah.
Okay, perfect. You're mapping over documents, counting words, then reducing with a sum.
Yeah.
That's great. Anything else? Is sorting included? Well, it depends on the algorithm, I guess. Definitely. You can do, I'm picturing radix sort. You could pretty easily structure this way. Definitely. Okay. So our example is, again, support vector machines, where you have this set of points, and you're trying to train this frontier. And the way that this algorithm works is that you have to find the distance of every point. You want to find extrema, so you find the distance of every point from the frontier. That's the function you're mapping. And you reduce to find the greatest, so your reduction is a max. And in the example I'll do later as well, in speech recognition, you're mapping over active states. You're mapping computation over active states to do hidden Markov model inference.
Can I ask a question?
Yeah, great.
So the difference between the first one and this is that each data thing has its own state?
The difference between pipe and filter?
Yes.
Okay, so
you're applying everything, but each filter has you're applying one filter but different states. Is that the idea?
Well, I think the idea is that these are independent.
Okay.
And they can be scheduled independently.
Okay.
So, and I guess I didn't mention that. That's a key part of the pattern, and that's what, Google MapReduce is all about fault tolerance. So these things can drop off all the time. Yeah, so that's really the key of the pattern.
All right, thanks. And the reduction is unique.
Okay, yes, so the reduction as well is not in pipe and filter. And it turns out, I mean, when you go to do parallel, I mean, yeah, you're all parallel programmers. You see this all the time. You have a huge data set and you want to do something and then reduce it. It's very common. And even in that, our iterative solver, this would be somewhere inside of that iterative solver as well.
So are there patterns which just map and not reduce?
So what we do with that is just call it a map with identity with no reduction. All right. Okay, fourth pattern. This is a good one. Agent and repository. So in a lot of applications, you have shared data, and you have a number of independent agents which want to act on that data. So you apply this pattern in which you have what's called a blackboard or repository that stores your data. You have intelligent agents that act on it. And the key is you have a manager that manages access to the shared data, and it also periodically checks to see if the data is consistent, if there's any format issues. So if one of these agents corrupts the data, for example, the manager will check this. So can anyone imagine an application that uses this type of structure?
Like barrier synchronization kind of stuff?
Barrier. Okay. So can you be? So what do you mean?
So like if there are 10 processors doing tasks on different kinds of data, but the final output requires the outputs from all 10 processors, then it has to wait till all of them are done.
Yeah, definitely. So what you're saying is that the manager would be in charge of making sure that.
Would,
Okay. So can you think more of so that's a very general example, but are there any specific applications that would use that type of structure?
Let's say if you're doing k-means clustering.
Okay.
So finally, you need all clusters to finally come up with feature vectors in terms of histograms of those k-means clusters, right?
Okay.
So for computing clustering, if there are multiple clusters involved, so you'll need the labels the k cluster labels to go any further than that.
Okay, so you're saying the cluster labels need to be shared, so they would be stored here,
Right.
and there needs to be synchronized access to get, because they need to be, yeah, okay.
Right.
Okay, that's good. Anything else? Banks. Okay, so that really, stretches, or not, sorry, not stretch, that makes good use of the manager. So I think what you're saying is the agents are making ATMs, so making transaction on the shared data, which is your balance, everybody's balances. And you want to be sure that those accesses are safe. That's a great example. Okay, so our example is compiler optimization. So this comes from Sweef, which is a Stanford optimizing compiler that does various loop transformations of vectorization. And you have your internal program representation, your loop nest, and you have all these optimizations that you could potentially do. You could get rid of dead code. You can remove things from the loop and do strength reduction. Do software pipelining. You can fuse loops or do loop fission and constant folding. So there's all these things you can do, but they impact the program representation. So when they're done, they need to check in the new IR. And the manager needs to make sure that the old code and the new code do the same thing and they still compile. And the other interesting thing is that there's heuristics as to how you apply these optimizations. So, so this gives you a level of abstraction that you can have a heuristic above it saying do loop fusion, now do software pipelining. And this gives you a sense that what you're doing is safe. Okay, pattern number 5 is, well, actually this is a pretty good one. So similar to the compiler optimization, there's logic optimization, where you store your circuit in the repository, and you can have independent agents which are applying circuit optimization techniques. So they're trying to reduce, the latency of a certain part of the circuit, or make it change from a ripple carry adder to a carry look ahead or something. So they can be working on independent parts of the circuit, and the repository manager in this case is very sophisticated, and will make sure that the circuit stays consistent across optimization passes. Okay, 5th pattern is process control. Here you have an underlying phenomena process that you want to control. It's shown up here. You have an actuator, which is your means of controlling the process, here. Sensor, which senses what the process is producing, and then a controller, which is your logic telling you how to manipulate the actuator. So there's a feedback loop where, based on what's being sensed, that affects your controller's decisions, and the controller then changes the actuators to try to make things more optimal. So what is kind of a classic example of this structure? Iron Man. How is that?
He has sensors and processes. The suit automates a bunch of stuff. We don't need a microphone. Certainly Jarvis is taking in data.
Yeah.
And running things.
Okay, that's a way better example than I thought it was going to be. Yeah. So. Yeah, so definitely a lot of sensors and a lot of complicated control, going into that. All right. Anything simpler that exists in the real world? Airplane. Okay, perfect. Yeah. So I'm picturing, you have your pitot tubes or whatever sensing your altitude. And that obviously goes into especially Airbus, very complicated controller that flies the plane for you. So that's great. All right, so kind of I was expecting a little simpler. The furnace thermostat, essentially it senses that it's not very, well, it's expecting more people in this room probably than we currently have. So it's probably pretty cold, and it has to fire up the furnace based on that. So that's kind of a classic example. But here's another one in software. So circuit optimization, we keep going back to that. You have a circuit, an integrated circuit description on your computer. It has constraints. Then you run things like timing analysis to get the frequency of the circuit, power, to get the power and the energy consumption of the circuit. That gets passed back to some higher level controller, which is going to launch those optimization transformations I was talking about, which are going to modify the circuit to produce different results. So that's one example. And then this is another one, more relevant to this class, I think, which is an auto-tuner. So this is specific examples from our lab, Aspire Lab, where there's a student who's trying to optimize matrix multiply for energy. So he has a source code he has a source code generator for matrix multiply. It takes in your problem dimensions. Depending on your dimensions, you're going to get much different behavior. He's able to manipulate that source code using block sizes and maybe in the future loop transformations. Then he runs the source code, uses the WhatsUp Pro to get energy numbers, so how many joules did it take to run that code. That's up here. Here's different runs. It's taking 90 joules and 70 joules. That gets passed back into this OpenTuner software, which does some machine learning to pick the next point that you should try, the next block size you should try. And then you give an objective function like minimize energy or minimize time. So I think this is a very relevant pattern, and it's used in software extensively, actually. Okay, so jump all the way to pattern 9 is the puppeteer. So the problem, again, these are problem-solution pairs. The problem is we need an efficient way to manage and control interaction of multiple, pretty complex simulation down here. So this pattern essentially says puppets can run independently, and when they need to communicate with one another, you have an entity called puppeteer, which will facilitate the interaction. So the puppeteer doesn't store any data, and that is a big difference between this and the agent repository. This, you're doing sort of a message passing interface, and all the data is stored in the puppets. Okay, so does this look familiar to anyone? Can anyone tell me an application that would kind of use this structure? Operating system. Okay, so what are the puppets and what facilitates the communication?
Like different processes would be puppets.
Okay.
And, like some kind of bus would be an interface.
Okay. Yeah, that makes sense. So I think essentially what you're saying is that the computer itself is a puppeteer, and the operating system is the puppet. Is the puppeteer. Okay, the system is the computer, the operating system is a puppeteer, and the processes are puppets. That's great, and they communicate through pipes and sockets. That's a good one. Okay, so how about a video game? So has anyone built a video game at any scale? Even a small? Yeah, you did. Is it hard?
It could have been.
Could have been. Okay. So we looked at a pretty, not a commercial video game, but Intel had kind of made a mock-up of what a commercial video game, essentially the components it contains. And you have these different subsystems, and for example, physics engine to compute collisions and to move objects around, graphics engine to draw those objects and map textures, AI to control non-player characters. So all of these engines were just enormous, and sometimes they're their own software product. There's independent physics engines that you buy. So the idea is your video game essentially uses a puppeteer pattern where it interfaces. You build an interface with all these subsystems and you manage the interaction. And that's good too, because you only have to create, if there's 4 interfaces here, you only have to create 4 interfaces as opposed to doing n² interfaces. So trying to build communication between AI and physics, AI and input, for example. There's another, maybe more relevant in this class, a Paralab application that was modeling the flow of blood through a blood vessel. So what they had was a fluid simulation, which was worrying about blood flow, and then they had a simulation that was worried about the actual solid blood vessel. And these were pretty much developed independently, and they had to build an interface between the two. And the interface had its own set of concerns, such as it had to consider the fact that the two simulations were running at different time steps, and other kind of domain-specific concerns. Okay, and so any questions about structural patterns? I showed, I think, 5.
Could you say how that impacts implementation?
How does that impact implementation? So I mean, it does impact implementation in that it encourages, I guess, modularity, but I think it mostly impacts documentation and presentation as well. So
are there any like software tools that you can plug in parts that would do some of these for you? Like there's a library for matrix multiply that sort of hides details. Is there anything like that?
yeah, I mean, I think it's so. Are there software manifestations of these patterns? I think it's hard. I think there are frameworks that codify these patterns, such as I didn't show it, but model view controller pattern. Basically, any web framework is going to be an implementation of that specific pattern. But I think it's very hard to, in general, codify the patterns because there is a lot of variation within them.
I guess MapReduce is an implementation of MapReduce.
Yes, MapReduce is a specific implementation, definitely. All right. Okay, so in terms of computational patterns, I'm not going to go through each one because you've done that in this class, so you're all experts in these different areas.
We're in the middle of the process.
Okay, we're in the middle of the process. But so as I understand it, each lecture in this course is going to give you a great introduction, and there's entire books written about these patterns. And the website that I give you at the end, I think we have a lot of these written up as well. Okay, so finally, I have an application, and I'm going to walk through how to architect it using the structural patterns that I showed today. The application is large vocabulary continuous speech recognition. Large vocabulary meaning, for example, English. Continuous meaning the way I'm speaking right now, so not discrete words, but just a full sentence. And speech recognition meaning it takes in voice input and produces text with the most likely sequence of words. So think Siri, but without any of the personal assistant logic. So our implementation is an inference engine-based system, which is very common, and it's used in these huge speech recognition projects like Sphinx, HTK, and Julius. It's a modular and flexible setup, which we'll show, and it is language independent, so you can train it. You do a lot of sophisticated machine learning to train a recognition network, which works on whatever language you provide. So what happens is you take your voice input, you do some signal processing, some FFTs, some inverse FFTs. You produce features, which are vectors of length 39. You have one feature for every 10 milliseconds of audio. Pass that into your inference engine, which references this pre-trained model of the language and of the sounds contained in the language, and then produces output. Okay, so at the very top level, what I showed in the previous slide is a pipe and filter. Voice input, feature extraction, inference, and words come out. That's the top level architecture. In terms of computation, computational patterns, this inference engine, we're going to focus just on this because that's where the majority of the work happens. We're solving it using a graphical model, specifically hidden Markov model, and doing the actual inference using dynamic programming. So if you were, if you were to go and look at this code, the first thing that you should do is read up on graphical models and dynamic programming, because those are the main computations. Within the inference engine, we're doing an iterative process. So for each segment of speech, for each 10 milliseconds, we perform an active state computation, which I'll describe in the next slide. It has 3 steps, and so that's a pipe and filter. And within each step, as I'll show, is a MapReduce. OK, so this is the inference procedure. We're doing graphical model. We're solving inference on an HMM, hidden Markov model. And we're solving it using the Viterbi algorithm, which is dynamic programming. So we're trying to find, as you do in an HMM, we're trying to find the most likely sequence of states in this network. So starting with observation 1, we initialize all of these states to be equal, or to be their initial probability, the probability that you're in a given state. And then we step forward one observation at a time and compute the probability of being in all of these states given the probabilities from the previous observation. And the reason we're able to do this pretty efficiently is that they use the Markov condition, which tells them that the probability of being in any state at time t is only dependent on the probability at time t minus 1. So observations are little chunks of sound that have been processed and turned into features. States is a concept from the HMM. I don't know if there's a specific intuitive way to describe them, but these are kind of HMM states. And the formula for computing the probability of a state given the previous states is shown up here. So let's say you're trying to compute the probability of being in state 1 for observation 3. That's equal to this formula up here. It is the max probability of all the incoming edges where you compute the probability of being in this state multiplied by the probability of that edge transition multiplied by the probability of this observation occurring in this state. So that's shown here. This is the probability of the previous state, green, multiplied by the probability of the edge transition, which is pre-trained. Yeah?
So are states like words here, or
Sta-
words you recognize?
States are not words yet because we're at a much lower level. We're just thinking of sounds or phones. So states kind of have like that type of, yeah. When we're done, once we get this path, we're going to use a language model to determine for that given set of states which words are most likely. That's a separate process. OK, so to compute the probability here, we look back at the green one. It's that probability multiplied by a pre-trained edge transition multiplied by the probability, observation probability, which is that you heard this observation given that state. And because there's multiple incoming edges, you have to do a max over all the possible previous states. And the sparsity of this graph, or the connectivity, is also determined ahead of time by training. OK, so structurally, this is an iterative process. We start with observation 1, and we go forward and build up this entire table. So that's this iterator here. Then we do 3 stages at each level. We gather our operands into a contiguous buffer. We compute observation probabilities, which is the probability of being in, the probability of hearing this observation given that you're in this state. So you do that for every single state, active state. And then you have to do a graph traversal. So that is going from here, from the previous observation into your current observation. So you have to traverse every one of these edges and compute the max at every new state. It's 3 stages. That's a pipe and filter. Now we want to architect each one of those filters. So that 0 gather operand is a map where for all the active states, we perform a function to gather them and put them in a format that's, that has good spatial locality. So that facilitates the use of SIMD. Next, we want to compute observation probabilities. So for all of your states, you compute the probability of that observation given that state. And the way you do that is using a Gaussian mixture model. So every state has a little trained GMM. And given the observation, it computes the probability of that observation given that state. That's another map where the function that you're mapping onto all the states is GMM evaluation. And finally, the graph traversal. You're going from all the previous states to all the new states. And you can either map over all the previous states, in which case you'll have to synchronize on the new states, or you can map over the new states and gather from the previous states. But either way, you're doing a map over states. And in this case, there's a reduction, which is a max reduction over all the incoming states. OK, so then to summarize, we started with this big blob that nobody really, you couldn't really understand what it was doing. We architected it using first pipe and filter. We identified the key computations, then architected the inside of each filter with an iterator, pipe and filter, and MapReduce. And what you were asking about the inference, once you have a path through this space, then it's an entirely new inference procedure to figure out what the correct word interpretation is. So in this case, these features produced a path that could either be interpreted as recognized speech or recognized speech. OK, so this approach, I mean, I can kind of tell you that it's a good way of doing things, but it's led to a lot of important speedups and a lot of successful implementation papers, especially in in application conferences. So these are a number of different applications that are all parallel. They're all emerging applications, and we're getting large speedups. And a lot of people are downloading and using the software as well and citing it. So that was our application, and just to summarize, this is the approach. Yeah?
Could you say a little bit more about how the speedups are measured?
OK, how are these speedups measured? So these speedups are very large, and they're measured by taking the code that is most commonly used. So for example, for let's see, for contour detection, they took the code from Jitendra Malik's group that is research code, essentially. So a combination of MATLAB and C++. And sequential. Yeah, exactly. This is sequential code running on just a general CPU. And pretty much all these papers are running on GPU. So they measured just application performance. And some of these, they're more efficiently using parallelism, and some of them actually are completely, they used actually different approaches to solve the problem. For example, and I'm sure you're familiar, the contour detection had a special Lanczos algorithm that didn't re-orthogonalize vectors, so forth. So there was a lot of optimization that went into these. All right. So in general, the approach is to start with a compelling performance-sensitive application. So I heard before we started that you're all submitting project proposals right now. So you're all doing this. And performance-sensitive is important because if we didn't care about performance, then why would we be parallelizing things at all? Next thing you do is identify software structure. So just go up to the whiteboard, try to apply those patterns that I showed. Identify the key computations, and then go and read either the pattern description or Jim's slides or the books about these computations. Then you compose computational and structural patterns to yield a software architecture and implement it. So this led to the development of kind of like Christopher Alexander's pattern language for architecture we made, and previous software architecture pattern language. We made a pattern language for parallel programming. These two components are what I talked about today. And then below that, in the lower levels of the stack, our colleague Tim Mattson wrote a book about how to actually implement these applications and different patterns for when you're actually, for example, using threading libraries and choosing hardware and designing hardware even. So in summary, computational patterns can make you feel smarter because it'll give you perspective. So if you understand, let's say you understand sparse linear algebra and graph algorithms very well, that gives you a huge part of computer science is you can classify using those two computations. So it gives you really a classification that might not have existed before. Structural patterns make you feel good about your software because it's organized and it's modular, and when someone asks you about it and you go to the whiteboard, it's not just a huge mess. And all of the advantages of modularity that we talked about. So specifically, our pattern language, what we're trying to do is document all of these approaches and techniques. Here's just the name of every one. You can see the ones we went through today. And if you go to our website, each one of these, you can maybe not every single one, but you can click a link and it'll have a full problem description pair. And there's kind of a standard format for how you document these. So as I said, over here is what we talked about with the computation. Here, this came from the Garland and Shaw book. And this is Tim's book on the bottom, which there's recently a new edition. So that is worth checking out. OK, so we talked about a good approach to writing parallel software. You use structural patterns, you use computational patterns, you use structural patterns to compose computational patterns, and this composition process really helps direct your development of parallel software in the right way. So as I said, this is our website where you can read more about all those patterns. And this is our research group's website, which has all the papers and all of our implementations that apply this technique. So are there any questions?
Let's thank the speaker. So the website has more examples of architectures.
Yes, definitely. The website has descriptions of each pattern, and then in the papers, I think and actually in the thesis of people who graduate, they do a pretty good job of taking their application and architecting it in this way.
So these can serve as models for people's final projects. It might help them get built better.
Yeah, that would be great. And if you do have an architecture that you're interested in sharing, we'd be happy to see what you come up with.
And also what we can do in office hours, or whoever's interested is try to do brainstorming on a whiteboard to see if we can break down your application into these patterns, and that might make it easier to do as a sort of a team effort than doing it all by yourself.
All right, thank you.